Dear students, Assalamu alaikum. Last week we studied about different type of flip-flops. JK flip-flop, SR flip-flop and D flip-flop. And now this week we are going to study about the application of the flip-flops. So I already told you last week one of the application is counter. So what is this counter? So if the flip-flop is connected in series, then it is called as counter. Because you just remind you that one of the application of JK flip-flop is counter. So again in a JK flip-flop there are four states. Just you remember that 0 0 0 1 1 0 and 1 1. So if the flip-flop when the input J and K are 1, that means 5 volt, then the output is in a toggle state. So this is the property which is used to divide the frequency. Okay, as I told last week, each flip-flop divide the frequency by 2. Okay, so now here this counter we have two important type of counters, or the counters are classified into two very important types. One is called asynchronous counter and another one is called a synchronous counter. Okay, so what is asynchronous counter? Asynchronous counter means the clock should be applied for the first flip-flop and the output of the first flip-flop is given as the clock for the second flip-flop. Okay, so it is called asynchronous counter. And by the way, the output of the second flip-flop is given into the clock for the third flip-flop. Okay, so here the clock is in a serial nature. Okay, this is otherwise called a ripple counter. But in synchronous counter, each flip-flop clocked simultaneously at the same time. So of course, which is fast? Synchronous counter is more fast. But one of the advantage of asynchronous counter is asynchronous counter, the circuit is very easy, no need for any additional gates required. But while as synchronous counter, we need additional circuitry. Each counters having its own advantages and disadvantages. Okay, so first of all we have to study about asynchronous counter. So here if you watch, this is the asynchronous counter, 2-bit counter. So 2 JK flip-flop. So see here, this is flip-flop 1 and flip-flop 2. So as I told you, the J and K are 5 volt, that means logic 1 and clock is given. Okay, then see here the second flip-flop, who is the clock for the second flip-flop? The output of the first flip-flop will act as the clock for the second flip-flop, and of course J and K logic 1. Okay, so this is a circuit diagram. This is called a 2-bit flip-flop. So since it is 2-bit, let me analyze the truth table now. See here, the truth table, see the clock is coming. So for 4 clock pulses and Q1 means the output of the first flip-flop, and we know that it is negative edge triggered flip-flop. So whenever the first clock is coming, as you know, the input of the flip-flop J1 K1, so it is going toggle state. So initially it is 0. So whenever the first clock pulse coming, it goes to toggle mode. So what is toggle mode? Toggle mode means the 0 will become 1 or 1 will become 0. Since initially it is 0, so it goes 1. Now now the second clock pulse coming, again toggle mode. Okay, that third clock pulse again toggle mode, and the fourth clock pulse again toggle mode. So see here, what is the input frequency now? How many pulses here? 4 pulses. So see here, the first flip-flop output only 2 pulses. So one flip-flop divide the frequency. It clearly shows that one flip-flop divide the frequency by 2. Assume that this is 4 Hertz. The output of the first flip-flop will become 2 Hertz. Now for the second flip-flop, as I told you, let me bring the slide again. See the first flip-flop. So second flip-flop, who is the clock for the second flip-flop? the output of the first flip-flop acts as a clock for the second flip-flop. Now again I will go to the timing diagram. So see here, now for this second flip-flop, this is not the clock. Q1 is the clock. So each negative edge, so this is the falling edge. Negative edge means falling edge. So here two falling edge, this one and this one. So each falling edge, the toggle mode happening. So initially it is 0. So this is the first falling edge toggle. That means 0 become 1, and this is the second negative tridge. So here again 1 becomes 0. So see here, since here 2 hertz, so it will become 1 hertz. Okay, so if two flip-flops are together, then we can call this as divide by 4 counter. Okay, first flip-flop will divide by 2 and the second flip-flop again divided by 2. So it is totally divided by 4 counter, or we can say that mod 4 counter. See the truth table here. See Q2 and Q1, the output 0 0 0 1 1 0 1 1. Then again it will go to reset. Okay, so this is asynchronous counter. Okay, or it is called mod 4 counter. Mod means modulus. Okay, okay. Now what is the how we can produce a divide by 3 counter, that means mod 3 counter, using JK flip-flop and other associate circuitry. So before that, what is this mod 3 counter or divide by 3 counter is? Let me tell the truth table. So as I told before, mod 4 counter has 4 states. What are the states? 0 0 0 1 1 0 and 1 1. But after that reset. But what about mod 3 counter? Mod 3 counter has only 3 states. What are they? 0 0 0 1 1 0 and then no 1 1. So this 1 1 will become reset to 0 0. So this is about mod 3 counter. Now the idea is, how can we reset, because how can we design this counter? Okay, again see the question. See here, maybe in exam the question will be like this: draw the circuit to produce a divide by 3 counter or mod 3 counter using a JK flip-flop, and we need of course associated circuitry or NAND gate is necessary. So we know that, see here, this is a first flip-flop and the clock is given to the first flip-flop because it is asynchronous counter. So the output of the first flip-flop will given as the clock for the second flip-flop. Okay, so here now they are putting a NAND gate. Why means, if you are not including NAND gate this circuit, then it become mod 4 counter. Okay, we don't want mod 4 counter, we want mod 3. See the question here, mod 3 counter. So we have to reset the fourth one. So let me go to the truth table again. See here, first state allowed 0 0 allowed, second state 0 1 allowed, third state 1 0 allowed, fourth state 1 1 not allowed. So we are in a position to make this 1 1 into 0. So how to become 1 1 into 0? Of course NAND gate will do that. You all know about NAND gate. If you take a 2 input NAND gate, if you give the input 1 1, of course the output will become 0. So see here again, so if this Q1 and Q2 1 1 come, that will go to this clear. So what will happen is, as I told that here, this is the preset and clear. Last week I told that what is the benefit of preset and clear. Preset is used to make the output 1 and clear is used to make the output 0. Since it is active low, so this NAND gate output is 0, it will reset the flip-flop. So now how in the truth table will be 0 0 0 1 1 0, then here again we have 1 1 become to 0 0. Okay, so this is about draw the circuit to produce divide by 3 counter using JK flip-flop and NAND gate. I hope you understand. Okay, so this is the timing diagram. So here in the exam, the timing diagram will be given, but you have to draw the output waveform Q1 and Q2. Okay, you have to draw. and of course the truth table is given. You have to fill the values 0 0 0 1 1 0 and this one. Okay, now let me tell you about see second question. For example, draw the circuit of divide by 5 counter using JK flip-flop. So here the first question is how many flip-flop we required to achieve this one, because if you have 2 flip-flop then we will go the maximum of 4, because 2 to the power 2 is 4. At the same time, if we have 3 flip-flop we can go to the maximum of 8, because 2 to the power 3 is 8. But here in the question, carefully see the question, it is divided by 5. Okay, let me go to the truth table. See here, see this is the truth table. So here 0 0 1 first state, 0 0 1 sorry 0 0 0 state 1, 0 0 1 state 2, 0 1 0 3, 0 1 1 fourth state, 1 0 0 fifth state. Only fifth state is allowed. Why? Because it is mod 5 counter. Then 101, of course this is the next state. We have to reset this fifth state into 0 0 0. So this is our aim. How to achieve this one? Like NAND gate, as we saw before. Again go to the circuit. Therefore they are putting a NAND gate here. So they will put Q1 and Q3. See here again the table here. See here we have to reset Q3 and Q1. See here Q3 and Q1 should be reset. They are not connecting Q2 because Q2 always 0. No need to reset again this one. So we have just reset Q3 and Q1. So here the NAND gate Q1 and Q3, and this NAND gate output will go to the clear signal. So assume that if you have no NAND gate then this will become mod 8 counter, but if you put a NAND gate with Q1 and Q3 it will become a mod 5 counter. It means that after the fifth state it will go to reset. See here the table, after fifth 5 coming, then after the 5 states it will automatically reset and then start again 1 2 3 4 like this. See the timing diagram here, very clear timing diagram. It shows that this is the clock pulses, and Q1, this is the flip-flop, output of the flip-flop. Each clock coming, negative clock, changes its state. See here, initially 0, it is triggering here. So toggling, clock 1 toggling, clock 2, then second clock toggling, third clock toggling. So it is toggling. Now Q2, who is the clock? This is not the clock. Okay. Q1 is the clock. So each negative triggering here, toggling happens. So here toggling happen, and this is the negative trigger, toggling happening. Okay. Now here this is the clock. So here this is the negative triggering, toggling happening. Okay. So see here it is very clear that 0 0 1 state 1 allowed, 0 0 0 allowed, 1 allowed, 2 allowed, 3 allowed, 4 allowed, fifth not allowed. Fifth not allowed. So fifth will become 0 0 0. Again it is start 0 0 1 and so on. Okay friends, this is the truth table and timing diagram of the mod 5 counter. I hope you understand. Now synchronous counter. So as I told before, counters are broadly classified into 2 categories. One is asynchronous counter, that just now we studied. Now we are synchronous counter. So just for your review, asynchronous counter means only one clock. So that is the first clock is given to the first flip-flop, okay, and the clock is going on serially. Okay. That means the second flip-flop, the output of the first flip-flop acts as the clock for the second flip-flop, and the output of the second flip-flop will act as the clock for the third flip-flop, and so on. That is why asynchronous counter is called a ripple counter. You know, ripple in water. If you ripple means it is going one by one. Okay. So it is low also, it is serial. So, but synchronous counter, it is very fast, because see here the clock is connected in parallel. Okay, the same clock going on each flip-flop. So it is very fast. Okay, it is very fast, but as I told you, the one of the disadvantage of this one I will tell later. First we will go for 2-bit counter using JK flip-flop. So this is JK flip-flop, and the clock is going simultaneously or by parallel. So it is very fast, as I told. See here, and both J and K tied to 5 volt high. But what is the difference is here and here the clock is same, but J1 K1 it is not 1. Okay, the output of the first flip-flop is connected to J1 and K1. The output of the first flip-flop is connected to J1 and K1, but clock is same. Clock is same clock. Okay, now let me analyze the table. The table and waveform are similar to the first flip-flop. Okay, so how can we analyze this one? This is how we can analyze is, see, for example, see the Q1. So Q1 is 0 1 0 1. Okay, so Q1, what is Q1 here? So here this is Q0. Assume that this Q0 here, it is Q0, not Q1, it is Q0. So here, see again here. Okay, so for the first flip-flop, this is a first flip-flop 0 1 0 1, because each and every clock toggling happen. Okay, so but second flip-flop the clock is simultaneous, but the input is not 1 1. So when will the input 1 1? That means I will tell you here. See here, here the input is 1 1. So each clock it is toggling. Okay, therefore we will get to the table like 0 1 0 1. But here this is J1 and K1 is not connected with 5 volt. This is connected with the output of here. Okay, so how this is working means, for example, if the first clock coming, assume that J0 K0 1 1. So here 1 1 means toggling. Okay, so first it is 0. Initially it is 0. So that means J1 K1 will be 0 0. So 0 0 means here no change. Okay, no change. Therefore see the table here. See the table here. See 0 0. Okay, not this is 0 1, because the input is 1 1 1. So each time toggling, but it is not each and every 2 times only toggling. Okay, 0 0, that means no change. Okay, now again go to here. Okay, now the second clock pulse come, again toggling. So this 0 will become 1. Now this is become 1 1. This is become 1 1. Okay, so what will happen is, see here the table here, 1. Okay, 1. Now what will now this is 1. Okay, so this is divided by 4 counter, synchronous counter, and this is divided by 4 counter. So this truth table will become it is not resetting, because there is no NAND gate here. So it is 0 0 0 1 1 0 and 1 1. So it will not reset. Okay, here it is 0 0. Okay, so this is the synchronous counter. So here it is 2-bit synchronous counter. The truth table is 0 0 0 1 1 0 and 1 1. Okay, the important difference, once again I am telling, the very important difference here is the clock is parallel. Okay, and here the input is connected here. Okay, J0 K0 is 5 volt, but J1 K1 is not 5 volt. This is the main difference here. Okay, now this is a 3-bit synchronous counter using JK flip-flop, synchronous counter. So here 3 flip-flop, because it is mod 8 counter. Okay, so of course see the clock, it is parallel. This same clock is going here and here and here. So parallel clock, and here the first flip-flop, the output is tied here. Okay, J1 K1, or the same input is going Q0, and J2 K2 both will going Q1 and Q0. So Q0 and Q1 will connected with an AND gate, and it is going here. Okay, so see here, this is the timing diagram is same as that of asynchronous counter, and the truth table is also same. Okay, that means 0 0 0 0 0 1. Here see the Q0. So for example, this Q0, this is Q0. So here J0, K0 connected to 1. So each clock, each changes its state. See the table Q0, 0, 1, 0, 1, 0, 1, 0, 1. Because J0 and K0 is 1. So each time it changes its state. For Q1, what will happen is for Q1, J1, K1 is not permanently connected to 5 volt. So this output here, so this output means not every time it changes. So every alternate times. Therefore, if you see here, first 0, then no change. After that, change. Then no change. Then change. Then no change. Okay, so every 2, so 2 0 and here 2 1, 2 0 and here 2 1. Not like, see what is the difference between here and Q0 and Q1 is Q0 the input J and K is connected to 1. So every time it changes its state. For Q1 it is not like that. So because there is a 0 1 0 1. Okay, there is a no change state is there. So first 0 0, then double 1. Okay. So 0, then no change. After that toggle. Okay, then no change. Then toggle. Then no change. Then toggle. Then no change. And going on. Okay. Now here another one is see this is the AND gate. So this one, when you will get 1 1 means this is depending upon Q0 and Q1. How we can explain means, for example, here this is the multiplication of this one. For example, 0 and 0. Okay, that means no change. So this is no change. Okay, 0 multiplication of 0 0 0. So no change. 0 1 multiplication 0. So no change. 1 0 multiplication 0. No change. 1 1 multiplication toggle. So here you will get to the toggle here. Okay, and then again what is the product of these two? 0. So no change. And the product of these two 0. No change. The product of these two 0, no change. The product of these two 0, so no change. Okay. So here y means this is see here again I am explaining the truth table. See 0 means no change, so the same 0. Here 1 means toggle, so here 1. Again 0 no change, the same. Again 1 toggle here. Now 0 no change, so 1 toggle. But here this is the product 0 0. What is the product of 0 0? AND gate will do the product. So 0 0, the answer is 0. So no change. Again 0 1. The product of 0 1 is 0. No change. Product of 1 0 is 0. No change. Product of 1 1 is toggle. So here it is changes its states. Okay. So these are the state counter state sequence for 3-bit binary counter, Shabab. Now the conclusion is. We studied about counter. There are two. This is the application of the JK flip-flop. Now the conclusion. I am telling about the conclusion. We have two type of counters: asynchronous counter and synchronous counter. So what is the main difference between asynchronous counter and synchronous counter? Asynchronous counter is otherwise called a ripple counter. Asynchronous counter, the clock is serially going. The clock is given to the first flip-flop, and the output of the first flip-flop acts as a input of this act as the clock for the second flip-flop, and output of the second flip-flop will act as the clock for the third flip-flop, and so on. But synchronous counter, the clock is simultaneously clocked to all the flip-flop. So synchronous counter is very fast than asynchronous counter. But regarding the access time, synchronous counter is fast. But circuit complexity, regarding the circuit complexity, if you go for mode higher mode, then the synchronous counter you have to make many big circuit, many complicated circuit with additional logic gates. So circuit complexity is more in synchronous counter, but it is less than asynchronous counter. So each have its own advantages and disadvantages. Dear students, I am planning to meet you inshallah inshallah coming weeks. That means week number I think week number 10. This is the week coming Sunday, week number 10. I am going to meet you through inshallah. I am planning to meet you by Blackboard Ultra Collaborate. Blackboard Ultra Collaborate. The same time, I have two sections. One section, Monday section, I will meet Monday period number 9 and 10. and another section Thursday. I will meet you Thursday 7-8. Inshallah, I am planning to meet you, and I will conduct a doubt clearing session for the 2 week lessons. Okay, flip flop and counter, and please attendance. Please all of you participate in the Blackboard Ultra session, collaborate session. I will give the announcement. I will put Blackboard the announcement. We will talk each other, and I will clear all the doubts. Okay, Shabab. Thank you for listening. Assalamu alaikum wa rahmatullahi wa barakatuhu.